We now move on to question number 4. An infinitely long hollow conducting cylinder with inner radius r by 2 and outer radius r carries a uniform current density along its length. The magnitude of the magnetic field B of r as a function of the radial distance r from the axis is best represented by which of the following graphs? So can you tell us the framework within which we'll go about solving this question?
Yeah, for this basically we'll use the equation integral of B dot dr equals mu naught I.
Alright.
That is the integral of B over a loop, closed loop.
Okay.
So through that we'll try to find at three various places what the function of Br is, or basically how it decays with the radius.
Right.
So let's start.
Okay.
First we draw the cross section of the wire.
Alright.
So here we have the origin, and this is r by 2,
Right.
and this is r.
Okay.
So let's consider for a distance x, for 0 less than x less than r by 2.
Right.
We do the usual, make a loop
Okay.
and apply integral b dot dr equals mu naught I. So b dot 2 pi x equals 0 because there is no current enclosed. This is all the hollow portion.
Okay.
So b be 0 हो जाता है inside because this is hollow.
Okay. So within the first portion, because there's no current enclosed, so ये जो इंटीग्रल लगा रहे हैं यहाँ पे आप उसमें like I 0 हो जा रहा है, so basically the whole magnetic field becomes 0.
Okay, yeah.
Right.
तो और क्वेश्चन में मेंशन है यूनिफॉर्म करंट डेंसिटी.
Okay.
तो अब हम एज्यूम कर लेते हैं कोई करंट डेंसिटी.
Okay.
मान लेते हैं.
So what is this current density? Like how do you define this?
Yeah, current density, like this is a cross section. If we are given a particular cross section of a wire,
Right.
and say the wire carries a current I,
Okay.
so the current density will be basically I divided by the area which is carrying the current.
Okay.
Like suppose the outer part is carrying the current,
Right.
so I divided by the area. It is basically the density is the areal density of the current carried by the cross section.
Acha.
So for this we have a current density J.
G.
Okay, so let's start. Let's see the case 2. This is that was a case 1 in which we were inside the hollow portion.
Okay.
Now let's look at case 2,
Right.
in which we look at the magnetic field outside, say at a distance small r from the center,
Right.
and such that r is greater than capital R. Small r is greater than capital R.
Okay.
So b into 2 pi r, because it will be uniform, we can directly write this,
Right.
equals mu naught into I. So I will be the current carried by it basically. So this will be J into
Okay.
pi r square minus pi r by 2 square, which is basically this area.
Okay. So we're looking at the current being carried within the cylinder, which is exerting a field over here.
So this is mu naught J into 3 pi r square by 4. B will be whole into 1 by 2 pi r.
Alright.
So its GK will be like this. The graph should be after r. The graph should be like this.
Okay.
Okay.
Correct.
And till r by 2, the graph will be like this, 0.
Okay.
Now we have to figure out from r by 2 to r.
Right.
Okay. That is the main part of the problem. Now we see case 3. In this case, we are looking at the part where the current is actually flowing.
Okay.
So let's say it is at a distance r, and now we apply a rule. So b into 2 pi r equals mu naught j y square minus r by 2 whole.
I'm sorry. Could you please tell me what the variable y is here?
Oh, I made a mistake actually. It should be r.
Okay.
I'll just erase that.
Right.
So this is our r square minus r by 2 whole square
Okay, correct.
whole into pi, because like we want the area b into 2 pi r equals mu naught into I. So this all is the I which is enclosed, pi
Right.
into capital R square minus this small r by 2 whole square.
Right.
So let's simplify this. Mu naught j pi r square minus r square by 4 into 2 pi r. So pi will be cancelled.
Right.
B will come out to be mu naught j r minus r square by 8. Mu naught j r divided by 2
Okay.
minus r square by 8 into mu naught j.
Right.
And here, because we carried over r, so r comes here.
Alright.
And so this is our formula. Now let's see what case we have which is actually compatible with this one.
Okay.
So this is actually r varies from r by 2 to capital R.
Right.
Okay. So let's see by calculus that what this particular thing could be.
Okay.
So we see dB by dr
Right.
come to be mu naught j by 2 plus r square by 8r square.
G.
So see, this comes to be greater than 0 for r by 2 to r.
Okay.
So the curve would be like the slope would be positive always.
Right.
And now we see d2b by dr2 0 minus say 2r square by 8r cube. So this comes out to be negative.
Okay.
Now this is important because the slope is decreasing. This tells us that the slope is decreasing.
Right.
Slope is always positive, but that positive value is decreasing. Hence it would be something like this.
Okay.
So by this basically we select a graph which is finally from 0 to r by 2 it would be 0. Then it would be something like this till r, and then it would decay like this.
Okay.
So D is the correct answer.
Right. So that was question number 4, where we start off the question with by looking at an infinitely long hollow conducting cylinder with an inner radius of r by 2 and an outer radius of r, which has a uniform current density which we take it as j along its length. तो हमें ये पता करना है कि magnitude of magnetic field है, इसका function of radial distance r from the axis को representation करने वाला graph कौन सा है?
So
Right.
finally D.
Yeah. So we have 3 different cases in over here. The first case starts off by looking at the question from like 0 till r by 2,
Yeah.
which is the hollow part, right?
Yes.
And the second part looks at the second case looks at the answer from
greater than r, greater than the radius,
Right.
the outside part.
So for the first case, the answer comes out to be 0 because there's no current enclosed inside
Yeah.
this, right? So for the second case, we apply the law,
Yes.
and then we get an answer and the graph which looks like this, right? So
Till now, this is what we know of the graphs. Then we move on to case 3.
right, then we move on to case 3, which is looking at the answer from the distance r by 2 till r. ये थोड़ा कॉम्प्लिकेटेड है बेसिकली, बट
because
इसमें जो करंट डेंसिटी का हमने कॉन्सेप्ट इंट्रोड्यूस किया था
हाँ.
वो बहुत हेल्पफुल हो रहा है, राइट? सो एंड देन वी डिफरेंशिएट द आंसर वी गेट, एंड this is basically to get the graph, right?
Yeah, basically because we have to use calculus here to get the right graph,
Okay.
the right curve.
Okay. So this is for the curve, and क्योंकि d square by b by dr square नेगेटिव आ रहा है, तो इसका क्या इन्फ्लुएंस ले सकते हैं हम यहाँ पे लिख
इसका मतलब है कि जैसे ये स्लोप है हमारा,
राइट
जैसे स्लोप है हमारा ये,
जी,
तो यहाँ पे जो स्लोप है ये ज्यादा है, फिर जैसे जैसे स्लोप डिक्रीज करता जा रहा है.
राइट,
स्लोप हमेशा पॉजिटिव है, मतलब ये tan थीटा पॉजिटिव रहेगा,
ओके,
बट इसकी वैल्यू डिक्रीज करती जा रही है.
जी
बेसिकली d2b by dr2 ये बताता है कि स्लोप किस रेट से डिक्रीज कर रही है,
राइट,
और ये नेगेटिव आ रहा है. इसका
जी.
मतलब स्लोप कर्व हमारा इस तरह का होगा.
जी. सो हमें जो कर्व निकालना था वो बेसिकली उसका आंसर इससे हमें पता चल जा रहा है, एंड द करेक्ट आंसर फॉर द कर्व इज ऑप्शन डी. We'll start off with question number 5. A loop carrying current I lies in the xy plane as shown in the figure. The unit vector k is coming out of the plane of the paper. The magnetic moment of the current loop is... So, can you tell us how we'll go about solving this question?
Yeah, this is basically an easy question. This is
Right.
just to generalize the magnetic moment of which you had found for a loop.
Okay.
This is just to tell that that can be valid for any particular loop lying in a plane.
Correct.
So we found out that the formula was for a loop m was n into I into a into n cap.
जी.
बट यहाँ पे हमारे पास एक लूप है, तो इसमें भी हम यही कॉन्सेप्ट अप्लाई करके मैग्नेटिक मोमेंट इसका निकाल सकते हैं, बिकॉज ये प्लेनर लूप है.
जी.
तो जिस तरह से प्लेनर लूप का हमने निकाला था उसी कॉन्सेप्ट से इसका भी हम मैग्नेटिक मोमेंट निकाल लेंगे.
Alright.
और ये होगा n इंटू आई जो करंट फ्लो कर रहा है इंटू एरिया होल इंटू के कैप. इसको एक्स वाई प्लेन में एज्यूम करके,
जी.
बिकॉज एंटी क्लॉकवाइज करंट है तो राइट हैंड रूल से जब फिंगर्स कर्ल करेंगे
अच्छा अच्छा.
तो
okay.
ऊपर के की डायरेक्शन में आएगा. तो 1 इंटू आई इंटू, अब इसका एरिया निकालना है, तो एरिया
तो ये तो इरेगुलर फिगर है बेसिकली, तो इसका एरिया कहाँ से निकल रहा है?
इरेगुलर बेसिकली ये कंपोज्ड है सेमी सर्कल से, 4 सेमी सर्कल से
जी.
और एक रेक्टेंगल से.
ओके ओके, आई सी.
सो एरिया रेक्टेंगल का हो जाएगा ए स्क्वायर प्लस एक सेमी सर्कल का रेडियस आ रहा है, बिकॉज ये पूरा ए है, तो एक का रेडियस है a/2.
ओके.
सो पाई 4 इंटू पाई इंटू a/2 होल स्क्वायर.
राइट.
सो 4 इंटू पाई इंटू a स्क्वायर बाय 4.
4 पाई.
Area is basically this into 1/2 because it is a semicircle, not a circle.
Okay.
We have to be careful here.
Right.
We might make a silly calculation mistake. Into 1/2, which is equal to basically pi a square by 2. So we add it here.
Right.
To k cap.
G.
So the final result comes out to be I a square 1 plus pi by 2 k cap
Right.
in the direction out of the plane of the paper.
Okay.
Now a very important concept is there. This question can be done in another way.
Okay.
Let's see like let's take this semicircle
Right.
and this square. So we can use we can visualize it as this carrying current I, this I,
Okay.
and this carrying current I here.
Okay.
So like when we look at it in this way,
Right.
then what we'll see is that let's put the other ones too. These are all the semicircles.
Right.
Like we have just divided the figure and separated it into parts.
Okay. So why are we going with this method, like, and not the first one?
Like yeah, because this is a plane, so the first one is basically a trivial question.
Right.
But we are going through this because let's say if we were given something like this, a semicircle was here, and then another semicircle was in another plane, and we had to find the moment.
Okay.
So in that case, like we had to use this superposition method.
Right.
If we have to find it, because we know only for a plane.
Okay.
So for this, what we do, we find the magnetic moment for each particular loop
Okay.
and then add it.
G.
And why this is valid? Because let's say if we combine all these, then this one and these currents will cancel. So it will result in net zero current here,
Right.
and same will all these. So basically we'll get the magnetic moment because of all these outer currents.
Okay.
But just so that this is a tool which we can use in case we have something like two currents in two loops,
Right.
basically in other planes.
Okay.
And this would be helpful in that.
So that was question number 5 for us, where we are given a current carrying loop and we had to find the magnetic moment of the current loop. We apply the formula for the magnetic moment, which is n dot I dot A dot n cap, and then we divide the whole figure into a square and 4 different semicircles. उसका एरिया निकालने से हमें टोटल एरिया मिल जा रहा है, which is a square pi plus pi a square by 2 in the direction of k cap vector, and we finally get a final answer, which is ia square into 1 plus pi by 2 into k cap. So that's question number 5. We move on to question number 6 now. Consider the motion of a positive point charge in a region where there are simultaneous uniform electric and magnetic fields, which are given by the values E is equal to E naught j cap and B is equal to B naught j cap. That is, electric field and both the electric field and the magnetic field are in the positive y direction. At time t is equal to 0, this charge has velocity v in the xy plane, making an angle theta with the x-axis. Which of the following options are correct for time t greater than 0? Option A, if theta is equal to 0 degree, then the charge moves in a circular path in the xz plane. B, if theta is equal to 0 degree, the charge undergoes helical motion with constant pitch along the y-axis. Option C, if theta is equal to 10 degree, the charge undergoes helical motion with its pitch increasing with time along the y-axis. And option D, if theta is equal to 90 degree, the charge undergoes a linear but accelerated motion along the y-axis. So we have to look at the path that is traversed by a positive point charge in a region where we have both electric and magnetic fields present, right?
Yes.
Okay, at the beginning of time, for the charge in consideration, the charge moves with the velocity v in the xy plane, and it's making an angle theta with the x-axis. So we have to find out the path that is being traversed by the charge after the time t greater than 0. So can you tell us how do we go about solving this question?
Yes, for these type of questions, the most important thing is being able to represent the motion and actually visualize it.
Right.
So for doing that, we'll take the help of a coordinate system.
All right.
So let's start with the question. Let's assume this is the y-axis. This is the this is x, this is y, and this is it. And
Right.
for the time being, since E0 and B0 are not given,
Okay.
we just assume E0 greater than 0 and B0 greater than 0. That won't defeat our purpose, as we'll see later on, and we'll justify
Right.
that even if any one of them is negative, then the
Right.
type of motion won't change, just the direction would change.
Okay.
So we'll come to that later.
Right.
For now, let's assume it is greater than 0. Now moving on to our first case. If theta equals 0 degrees,
Right.
basically it is moving here. We have E0 here, and we have B0 here.
Right.
Okay. So basically B0, had E0 been 0, the motion would have been circular, because Q into V cross B, force would have come here and would have moved here
Okay.
somewhere.
Right.
But because it is not the case and E0 is there,
Right.
so if we look, like the motion will be starting from here, it will go up
All right.
with an increasing pitch.
Right.
Now, so this is not correct because the charge does not move in a circular path in the xz plane.
Okay.
Now let's see if basically E0 had been less than 0, this motion would have gone down,
Okay.
and if B0 has been less than 0, then instead of rotating here, it would have started from rotating there
Right.
and gone.
Right.
And likewise for the other cases in which like E0 less than 0 and B0 less than 0, both and other. So through this example we have seen that like E0 greater than 0 or less than 0, or B0 greater than 0 or less than 0 does not affect the type of motion.
Okay.
It will just affect the direction in which the particle will curve.
Right.
So-
So the magnitude of E and B don't make a difference overall, except for the direction.
The overall motion,
Right.
if it is not 0, but because it is not stated in the question that E0 or B0 might be 0,
Right.
so we will just assume it to be some value.
Right.
Now seeing the second one, if theta equals 0, the charge undergoes helical motion with constant pitch along the y-axis.
Okay.
So what we said was there, yes, we saw that it was going a helical motion,
Right.
but the pitch won't be constant. Now why
Okay.
so? It is because, see, an electric field is there.
Right.
An electric field would accelerate the motion.
Okay. So the electric field produces a force. Acts.
Yeah, and that the motion and the velocity will continuously increase.
Right.
Hence, the pitch would also increase continuously. And
Right.
the motion would be somewhat like this, with the pitch always increasing.
All right.
Now we come to C part. So the second part is also wrong.
Okay.
For theta equals 10 degrees, charge undergoes helical motion with its pitch increasing with time along the y-axis. Okay. Let's see what this is. So B is here along y. Suppose this is 10 degrees. Now as we had seen in for this question, let us divide this velocity into two components.
All right.
Okay. So one is the Vx, one is Vy.
Right.
This is the z-axis. So Vx is basically perpendicular to the z-axis.
Okay. And this is the velocity component on which the magnetic field acts, right?
Yes.
Okay.
This is a E0 and this is a B0 vectors. We draw them
Right.
too. Now, if we see for Vx, basically what happens is that because of this component V cross B, the force acts and basically in the z direction. So it will undergo a motion
Okay.
in the z. Basically V cross B, we write I cap cross B j cap. This is V perpendicular or the Vx. This will be some VB cos 10 degrees into Ij
K cap.
k cap.
Right.
Force acts in this direction. So basically this force should move it in a circle
Okay.
But because it also has a velocity,
Right.
so because of this velocity, it moves along the this y-axis,
All right.
and since E0 is there, so this E0 increases the pitch
Right.
because the velocity in the y is also increasing with time.
Right. Right.
So because of that, it undergoes a helical motion with increasing pitch.
Okay.
So this option comes out to be correct.
Right.
Now if theta equals 90 degrees, the charge undergoes linear but accelerated motion along the y-axis.
Okay.
Now this seems to be easy because our magnetic field was along y, our electric field was along y, and if particles also moved here, in that case like theta would be 90 degree.
Right.
So basically V cross B would come out to be 0.
Okay.
Because the direction of V and B are same. So no magnetic force will act.
Only the electric
Since
field.
only the electric force is acting, it will accelerate the motion,
Right.
accelerate the particle, hence it will move linearly along the y-axis
Right.
with the increasing velocity,
Okay.
hence accelerated motion.
Right. So option D is also correct for us, right?
Yes.
Okay.
So basically option C and option D are correct.
Right. So we looked at the different cases for which we had to solve this question, and we find that the first two options are basically not correct, as we showed so. If theta is equal to 10 degrees, the charge undergoes helical motion with its pitch increasing with time along the y-axis, and this is on the account of the magnetic field acting on the component of the velocity of the charged particle, right?
Yeah, with theta equals 10, there is a component,
Right, right.
and that basically had no electric field been there, it would have moved with a constant pitch, but
Okay.
the electric field increases the velocity in the y direction also.
Right,
Basically the time it takes to complete one circle
right.
decreases, and hence the
So because of the presence of the electric field here, the pitch increases with time along the y-axis. Also, we look at option D, wherein theta is equal to 90 degree. In this case, there is no magnetic field acting on the magnetic force acting on the particle.
yes.
Right. So only the electric field acts, and
Yes.
this produces a force. And as a result, the charge undergoes only linear but accelerated
Accelerated
motion
motion.
along the y-axis. So that was question number 6 for us.